Let's talk about the Zeroth Law of Thermodynamics. Now the Zeroth Law, it's a strange one. For one, it's called the Zeroth Law, and that's kind of weird. We'll talk about why in a minute. And for two, when you hear the actual statement of the Zeroth Law, it sounds so obvious and trivial, you think it's kind of stupid to have a law for it. In fact, when I first heard it, I thought it was pretty dumb. But now that I know a little more, it's not quite as trivial as I thought it was, and I'll try to explain why it might not be as trivial as you might think it is. So what is the Zeroth Law? It has to do with thermal equilibrium. And to demonstrate thermal equilibrium, let's say you had a piece of pie, key lime pie, and you also had a steel sphere. And we're going to take this steel sphere, and I'm going to place this in thermal contact with the pie, which is to say they can exchange heat. And which way is the heat going to flow? We know the heat will flow from the hotter object to the cooler object. Let's say our pie was in the freezer. It's nice and cold, and our sphere was sitting at room temperature, so it's the relatively hotter object. Then we know heat will flow from the hot object to the cool object, which is to say heat will flow from the steel sphere into the pie. But this net exchange of heat stops at some point. At some point, the sphere heats up the pie enough that no net heat is transferred one way or the other, and basically, you just have a pie and a steel sphere sitting there, and no net heat is transferred. And when that happens, when no net heat gets transferred between two objects, we say they're in thermal equilibrium. So that's all well and good, but what does this have to do with the Zeroth Law of Thermodynamics? Well, let's say you did this. You had your pie and your sphere, and you waited until they came into thermal equilibrium, and now you insert a third object into the mix. Some small amount of water, or a large amount of water, doesn't actually matter, but some water over here. And so after allowing the pie and sphere to come into thermal equilibrium, which is to say they don't exchange any more heat, you bring this sphere over here, you put it in contact with the water, and for the sake of argument, this doesn't usually happen this way. For the sake of argument, let's say no heat is transferred either way over here. So 2 is also in thermal equilibrium with this water, with 3. Usually you'd have water at some different thermal state and they would exchange heat. But for the sake of argument, let's say that no heat's exchanged over here. That begs a question. You say to yourself, wait, so 2 is in thermal equilibrium with 1, no heat transferred. 2 is in thermal equilibrium with 3, no heat transferred. What if... Now you start thinking and you ask, what if I put 3 in contact with 1? Will there be any heat transferred? That's the crux. That's the question that the Zeroth Law of Thermodynamics addresses, and the answer is no. No heat's going to get transferred here either. So the Zeroth Law says that if object 1 is in thermal equilibrium with object 2, and object 2 is in thermal equilibrium with object 3, then object 1 is also in thermal equilibrium with object 3. This is the Zeroth Law of Thermodynamics, and you can see some of you out there are probably thinking, well, duh, how could it ever not be like that? If 1 is in equilibrium with 2, and 2 is equilibrium with 3, then 1 has to be in equilibrium with 3. Well, yeah, I mean, it is like that. Our universe is like that. But think about it a little harder. You could probably think of a universe where it might not be like that. Imagine a case where, let's take this water, separate these all again. Imagine a crazy universe, which is not ours, where for some reason steel and pie, thermal equilibrium, no heat transferred. Steel and water, thermal equilibrium, no heat transferred. But water and pie, well, not thermal equilibrium. Heat does get transferred. This would be terrible. This would be a horrible universe to do physics in, because now you'd have to have some separate definition of temperature depending on what type of material you have. There'd be a key lime pie steel sphere temperature together, and there'd be a steel sphere and water temperature, and there'd be a water and key lime pie temperature. It'd be horrible. But our universe does not behave that way. Our universe follows the Zeroth Law of Thermodynamics, and the best part is that this allows us to define a universal temperature scale. Because temperature is defined to be the thing that's the same between two objects when they're in thermal equilibrium. In other words, the Zeroth Law makes it such that I could say this pie is at a temperature of 20 degrees Celsius, and this sphere is at a temperature of 20 degrees Celsius, and this water is at a temperature of 20 degrees Celsius, regardless of me telling you beforehand which two I'm going to put in contact with each other. If If I tell you these are all at the same temperature, you know. Put any of them in contact, no net heat's going to transfer between them. If the zeroth law didn't hold, you wouldn't be able to do this. You could say that, okay, the pie and the sphere are at the same temperature, 20 degrees. And you could say that the sphere and the water was at the same temperature, call it 20 degrees if you want. But the water and the pie would not be at the same temperature. You couldn't call these both 20 degrees. You'd have to have separate scales, and that's why this would be horrible. That's why you should respect and love the zeroth law of thermodynamics. But why is it called the zeroth law of thermodynamics? Well, physicists had been working on the first law of thermodynamics for a long time. They got that pretty well nailed down. Only later did they realize, wait, this whole endeavor of thermodynamics is kind of relying on the ability of us to be able to define a universal temperature scale between all materials and objects, and that's kind of more fundamental than even the first law is. So they realized we should give this a number previous to the first law, but the first law was already the first law, so we call this the zeroth law of thermodynamics.